Earthlings, if you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. We've been at it for a while, first getting the double-locked microwave link up and going, then progressively getting ranging voice up, voice down, and television going.
Hello, this is Houston.
TV from the moon! It was a struggle to get the first digital link going in the Earth to spacecraft direction, the up data link as NASA called it. It took us forever to reverse engineer the mysterious up data link test box, recreate boards that were missing, and crack the sub-bit encoding scheme. But we eventually succeeded in sending digital commands to turn on things like the abort light or punch key codes into the disk key, which is how NASA controlled the computer from Houston. Of course, there was a second digital link in the other direction, a much stronger one at that, the PCM Telemetry downlink. PCM stands for Pulse Code Modulation. In contrast to the standard FM telemetry of the time, which was analog, PCM was purely digital. The PCM telemetry was implemented by this large box that we have had sitting in the back for the longest time. It's one of the heaviest pieces of Apollo-Com's electronics. You can tell by its many connectors that it was connected to a lot of things in the spacecraft. And indeed it was. It transmitted 365 analog signals, 304 digital signals, plus a serial link stream from the Apollo guidance computer. This is the box that filled up the mini Houston control room screens with data, and let the controllers know what was happening with the spacecraft in great detail. We'll explain it with the help of much elevator music as we go, but we can't resist to open it up and take a look-see inside first. Ready for the big reveal?
Yeah.
So which is this box?
This is the PCM.
Alright.
Pulse
This is
Code Modulating.
the one that is the data down.
Yep, data down.
All the stuff that
Many connectors on top.
Ooh.
That's a lot of wires. And they're different box or different modules.
Yeah, it's not really what I was expecting from.
So this
The
is made by
radiation
radiation logic, and
Fancy printed circuit boards.
it is the most complicated bit of digital electronics, and it has no ICs in it.
Oh, danger high voltage.
So this is what I expected. It has to be super compact, and it's made with similar module to the Motorola one, except it's radiation logic.
They're like different kind of modules, and the pinouts seem kind of random.
Yeah, they're not the same, obviously, but similar technology, right? Podded gates is the pre-IC thing. And radiation logic was famous for making some of those, right? I have some ground ones, actually.
And then here's a big module.
So yes, the Apollo PCM telemetry was a novel and ambitious system, a significant advance in airborne digital telemetry. It was extremely fast for its time. In high bitrate mode, it could transmit at 51.2 kilobit per second from lunar distances. In fact, it was transmitting so much data that the remote tracking station could not relay all of it back to Houston in real time. So while the entire data was stored on a computer at the receiving site, say Honeysuckle in Australia, Mission Control picked a subset small enough that it could be transmitted live over leased phone lines and a pair of state-of-the-art Bell 201B 2400 bit per second high-speed modems. Remember, that's the time when a standard Bell 103 modem was speaking at 300 bauds. For a digital transmitter of the speed and complexity, which also had redundant circuitry, you'd think they'd jump at the chance to use the recently introduced integrated circuits, like the Apollo guidance computer people did. But no. The subcontractor responsible for our PCM box, Radiation Inc. of Melbourne, Florida, later part of Harris Semiconductor, was wary of the newfangled IC's availability and reliability. Instead, they stuck to their tried-and-true logic modules built out of discrete components. I own a few Radiation Inc. modules, the civilian kind not made for flying. They implement simple things like AND gates and flip-flops. But for the Apollo PCM, specialty modules were made using cordwood construction, where discrete components are sandwiched between two PCBs. They were then potted with a soft polyurethane foam, then assembled on larger PCBs. Finally, the PCBs were wired together into a book-like structure. And the result isn't bad, although remarkably heavy, at 20 kilograms or 44 pounds and 21 watts of power consumption. It's a two-person operation to lift it on the bench. Now, to be fair, there is evidence that Radiation Inc. also developed a much smaller IC-based PCM box that they called the Micro PCM. It transmitted only 100 analog channels, but this document dating from 1965 says that it weighed only 3.1 pounds and consumed 2.5 watts, a small fraction of our discrete PCM. I don't think it was flown in Apollo, but Radiation Inc. was certainly working on the next integrated version in the mid-1960s already. And this is what flooded the control room with all the numbers. Yeah,
so are these 4-layer printed circuit boards?
Do you think there are more than two?
Yeah, I see the top one, the dark one, and then the faint one.
Maybe 3
What is
layer?
the faint one?
The vertical.
You're seeing the bottoms of the modules.
Ah. So maybe it is just a 2-layer.
Okay. Oh, these modules are big and rectangular. They're like
Super potted.
Yeah,
they're wider.
There we go.
Very nice.
So it wasn't
those modules.
stuck like on the UDL. Those are large modules.
202, 202. Oh, these are all the same. Different serial numbers. I wonder what that stuff is made of. It's this sort of foamy looking plastic.
Is it soft? Yeah, it's not very hard.
Looks like hotel soap.
Yeah. So on the UDL, this was stuck to the bottom by the conformal coding, so we couldn't do this. Similar.
Oh, we've got different part numbers.
Yeah, you're right. 217, 216. It's also interesting is if you look at the board here, they have the escape pre-routed, but there's no trace attached on many of these. So they have the pad and then they have a little line, but then it just stops.
And it's all these wires are just soldered directly to the board. There's no connectors there.
That's why they put the silicone in, right?
Yep, to hold all the wires in place.
I later found a reason for the soft polyurethane foam potting in an early design review document. It was meant to prevent acoustic amplification of vibration at resonance, a real issue with all these heavy modules on large PCBs. It reduced the level of vibrations in the 200 to 500 Hz range by a factor of up to 5. The same document also sheds light on the connectorless design. Connectors were originally used, even mandated, to permit in-flight module replacement by the astronauts. But it was found that the large multi-pin connectors negatively impacted reliability and weight. After the Apollo 1 fire accident, when the in-flight repair requirements were dropped for Block 2 in favor of hermeticity, the connectors were eliminated and replaced by hardwire connections.
Well, this whole stack is loose now. So
Okay, the whole thing is going to come apart.
like pages of a book.
It's like the Soyuz clock.
Yeah.
I noticed that there are grooves on top of the modules here that line up with the pins on the adjacent board. So it can fit
So that's
flush.
why it fits completely flush.
Completely flush.
Everything's being
You
optimized.
get little divots right here and here for some of the corner pins here and here.
Wow. This thought about everything. Fantastic! Our PCM box appears to be in good condition. Let's see if we can make it work. The first difficulty is that we don't have the pinout and there are sure a lot of connectors and pins. The second issue is that we don't have the original hardware to decode the PCM telemetry stream. That would be a room full of equipment. So we'll have to build our own modern PCM decoding hardware. And for that, we need to understand the PCM data stream structure. Here is a high-level view. A telemetry cycle repeats every second, a cycle that NASA weirdly calls a subframe, although it is nothing but sub, it's the overall structure. In high bitrate, that so-called subframe, or 1 second of telemetry, is divided into 50 smaller data sets called prime frames. Looks like they have their naming backwards. Anyhow, we get 50 prime frames per second. We'll soon see that the prime frame is the basic telemetry unit that we need to decode. Furthermore, a prime frame itself is composed of 128 words, with a word being just the usual 8-bit byte. We find more details about our prime frame in this intimidating PCM block schematics drawing. The prime frame structure is described in symbolic form in a table at the left. That table title says HBR format. HBR stands for high bit rate, which should be 51.2 kilobits per second. Here it says 6400 words per second instead. Indeed, 6400 words per second times 8 bits per word makes the expected 51.2 kilobits per second. It all checks out. We see that each of the 128 data words within the frame is described by a square, number 1 to 128. Let's take a closer look at the first 4 words. We see sync 1, sync 2, sync 3, sync 4, and frame count. Aha, this must be the sync pattern for the beginning of the frame. This is a mainstay of serial protocols. There is always a unique bit pattern somewhere to identify the starting point in the continuous data stream. In modern protocols, such as Ethernet, the sync pattern is guaranteed to be unique. That is, the data that follows is encoded in such a way that the sync pattern never appears in it. But they didn't bother to do that for Apollo. The data payload after the sync is transmitted in clear, so the sync pattern can reappear in the data by accident. They simply chose a sync pattern long and unusual enough, 26 bits in our case, that the probability of false syncs appearing in the data was acceptably low. If it ever happened, too bad, you'd get a frame of bad data which you'd ignore and resync on the next frame. Anyhow, back to our sync pattern. In order to find the beginning of the frame in our new hardware, we need to find out what the bit pattern exactly is. The drawing tells us to look at 51DP1A, 1B, 1C, and 1D, which are the hardware blocks generating these words. We can find them over here on the block schematics. And sure enough, now we can see the sync bits. Sync 1 is hardwired to 000000101, sync 2 is 011110001, sync 3 is 10110111. Word 4, generated by cell 51DP1D, is more complicated. It starts with the last 2 bits of the sync pattern, both ones. But the last 6 bits are wired to the redundant frame counter, which counts our prime frames from 1 to 50. So here is what the beginning of each prime frame will look like. 26 bits for the sync pattern that we need to recognize, followed by the frame number. If we can recognize this pattern in the stream, we'll have found the beginning of a frame and identified its number. Next, I want to point your attention to word 20. It says SRC0 and SRC1. It also has a bunch of letter references in the margin and points to note 7. If we go over to the schematics and look at the SRC0 block, we see that it is simply hardwired to all zeros. Similarly, the SRC1 block is hardwired to all ones. These are test words of all zeros and ones that are used as health checks. Looking at note 7 tells us that these check bytes appear only in certain frames. SRC0 appears every 5 frames starting at frame 2. So our 0 word will appear in frame 2, 7, 12, and so on. Similarly, SRC1 appears every 5 frames starting at frame 3, so 3, 8, 13, and so on. Which is what the letters C and D in the margin are meant to indicate also. So if we manage to build some hardware that can find the sync pattern, read the frame number, and read the test bytes, we should be able to do a health check on our PCM box. Fortunately, we have Mike Stewart in the team. Mike is the master of all things FPGA. Hell, he made a full Apollo guidance computer replica out of an FPGA. So one day he showed up in the lab having built an FPGA PCM decoder for us. So piece of cake for Mike and probably for all of you viewers and FPGA wizards to build a PCM decoder. You can even grab Mike's code on GitHub in case you need to be ready to decode Apollo telemetry during their next mission. However, the next challenge was to find and hook up enough of the PCM power and control pins so it would start transmitting. In normal usage, the PCM gets its critical clock and timing signals from the CTE box, the central timing equipment. It gets a reference 512 kHz clock and a 1 pulse per second tick that starts the 50 prime frames. However, the PCM has a failover oscillator that takes over in case of a CTE failure. So if we just power up the PCM without hooking it up to the CTE, it should detect a CTE failure, revert to its internal oscillator, and start to transmit on its own. Did I already say that we did not know the pinout either? Fortunately, we found an older drawing that gave us enough of a hint to identify the 115 volts 400 Hz 3-phase power inputs, of which there are 2 redundant sets. Except that this drawing also shows a neutral phase and we have no such thing in our Block 2 setup. You see, we don't entirely trust this early set of schematics. The pins for our transponder, for example, appear there and were mostly wrong. But we might be lucky this time, and the changes between the early and final flown versions of the PCM were less drastic. By measuring the impedance of the power pins, we were able to confirm that they were leading to a 3-phase transformer, and neutral should not be needed. So we are pretty confident that we identified the correct power pins. We could also identify one of the output pins, which is part of an easy to identify coaxial connection on J18, so that's likely correct too. We should now have enough to attempt our first power up. So it's another day with the Apollo setup, and we are trying telemetry down for the first time.
Okay.
And Mike, you're trying to decommute the data, as it's called, the telemetry data.
Yeah, so I have an FPGA running over there that is able to lock onto the sync pattern in the PCM telemetry stream and byte align it. That's sent to my laptop over a UART, and then I have a Python script running over here that again locks onto the sync pattern and identifies 128 byte frames in the stream, decodes that into all of the different measurements, and then packetizes that and sends it to this command and telemetry server where we can look at the data coming off of it.
So it's a very simple hookup. We just power it up from our fuse box, which is hidden back there, and then we get the signal out and it runs on its own.
Okay.
That's
So
all
this is
the...
good. These are PCM health check words that are supposed to be 0 and 255.
Where are you guys? Wait. Say that again?
So SRC, I don't know exactly what it stands for. It's like the scale range check or something like that. I believe they're feeding in to their ADC something below 0 and above 5 and expecting it to put out 0 and 255. So...
Oh, so this is correct. This is a good test readings.
For us not feeding anything at all into the PCM, these are like the most, I guess, meaningful things in the data stream.
Okay.
Other than if we look at the 51 DP, which is 50 hertz parallel digital data. 51 DP1 is going to be our frame number. Well, it's the sync pattern plus the frame number. So we should, if I...
This is Chinese to me, but okay, fine.
Yeah. So you can see our frame number increasing and wrapping around.
Okay, so we're getting the frame number correct, at least. Okay. So here is the data coming out of our PCM box. Looks dirty. There you go. Oh, I see bits. I remember you had it. That's why you had the screen where you had the count coming down.
Yeah, zoomed in.
Right. And you can look at the place where it's over here. There, it's counting.
Yeah.
Yeah. So this is the frame count.
Mm-hmm.
Right. So it's counting frames.
We could try a real power supply.
Yeah, we only get I have a power supply at one of the HPs, and
Okay. What happened?
all of a sudden the quality of the signal went up.
Yeah, I noticed my FPGA lost lock, and I wiggled the cable around a little bit, and now it looks a lot better.
Oh no, it's this. It's your fake connector over there.
I see.
It's
Unreliable.
this little guy here.
Showing a
This is
little
not the best connection. I think that's.
Yeah.
Well, let me not touch it. We have beautiful signal. Okay, so that's much better looking.
Okay.
So here we go. We have a clean signal. And I see some other thing that's moving over here.
So that you're seeing the SRC check, switching between 0 and 0000, like all zeros and all ones.
Oh, that's the 0 and 255 readings. So that's a check that your telemetry is actually working.
Yep.
And that's the frame pattern. That's the sync pattern.
That should be.
Yeah, just before the frame count, right?
Yeah. So
Yeah.
it should exactly match the sync pattern shown in this study guide.
So it goes there, one long bit, then 2 large bits. Yeah, it does match.
If it didn't match, the FPGA wouldn't be able to lock on
Right,
because
so-
this is what I programmed it
So
to.
it is that. Okay.
If you go back to the data here, the reason it looks like that is this little blurb here. With the 0 volt input, the converter generates the binary equivalent of the decimal 1, 0000001. All input values above 4.9 volts will produce the binary code of 111110. So
we're singing 11110. So
that's what this is.
so when it's floating, it's high.
Apparently, yeah.
But the grounding didn't work. I think there should be step.
We should try putting some voltage in it.
Yeah.
Okay. Why don't we do that after lunch?
Yes. Let's do it after lunch.
Well, that's a good start, I'd say. The PCM powered up okay, Mike's FPGA was able to recognize the sync pattern and read the frame number. We see it incrementing from 1 to 50 every second as expected. Moreover, we decode the SRC0 and SRC1 test words, and they read 0 and 255 as they should. But we barely scratched the surface of the PCM system. We have much more to discover and explain. We'll need to devise a way to discover the input pinout, understand more of the PCM weird circuits, including its crazy analog multiplexing circuits, which relies on core logic and a semiconductor device I had never heard of, the INCH. Then we'll need to integrate the PCM into our setup to send the stuff over the air, and make an improvised PSK demodulator to recover the signal on the Earth's side. After which we'll be able to play mission control and do things the very same way it was done in the real missions. So we'll get back to you right after lunch, and get a good lunch too, so you are ready for the next episode. See you then!